Okay. So the next, I want to talk about, before time runs out, I want to talk about the next couple of experiments. So Thursday's lab, experiment number 2 is about purification, techniques of purification. Obviously a very important issue in the chemistry laboratory. You know, one of the things that organic chemists, a lot of organic chemists are engaged in are, say, in the pharmaceutical industry, so that the lab created products there have to be very pure for human consumption. So running a reaction in the laboratory, creating a substance and just leaving it there, that's not good enough, because it has to be purified and cleaned up. So this experiment number 2 for Thursday is a lot of talk about purifying stuff. And what the teaching fellow will do with you there is, it's, again, just like all of our experiments, a guided inquiry where you're going to be watching some videos, and you're going to be discussing some of the issues involved in the purification of this, that, and the other. Okay, so why would we need to purify anything in the first place? You mix A and B together, it's a reaction, they react together. Isn't C the only thing that is formed? Oh heavens, no. We have to remove unwanted materials. So A plus B goes to C. Yeah, that's the reaction that we want, but it's not just going to be C alone, because what else is in there is left over A. Right, the reaction does not proceed normally. Most of them do not proceed in 100% yield. So you're looking for C, but in the reaction mixture, you have leftover A and B, things that didn't react. That has to be taken out of there. Another thing that happens is that we want to get rid of residual solvent. Many of these reactions that we run in the laboratory have solvent in there. You have to get rid of that as well. Another thing that can happen is that you get C, but you also get byproducts of the reaction. A and B get together, they form C, but they could also form D and E and F and all of the other letters of the alphabet. And not only that, but this guy here, and this guy here, the reactants that we started with, they may have come from an old bottle, right? These may be contaminated already. These may have had some kind of contamination in there already at the start of the experiment. So we're going to get C, leftover A, B, solvent, byproducts, and maybe some kind of impurity, some of the impurities in A and B. So so you're running a reaction in a laboratory, you're creating a lab-created substance, but you're not going to get 100% yield of that substance. It's going to be a complicated mixture of that has a lot of stuff in it. So this lab experience, as we're calling it this semester, is about talking about how to purify stuff. And so I just explained why we would need to purify anything in the first place. Okay, so major techniques in purification. It depends what the system you're trying to purify is. So one of the techniques for purification is liquids. And here, the technique that is used to purify a liquid is distillation. 2 L's? Distillation. I think it has 2 L's. Distillation, where you have a mixture of a bunch of liquids, and you're going to heat one of the, you're going to heat the mixture. So we have this little, can draw this little picture here. So you have a flask, and then you have a receiver. And this receiver is going down into another flask down here. And in here you have a mixture of A, which is a liquid, and B, which is a liquid, and so on and so forth. And what we do here is we heat this mixture. And as the liquid mixture absorbs this energy, the molecules begin to move around. They begin to move around and begin to vaporize, go into this vapor phase, into this distillation flask. So after a while, you get a bunch of gas molecules in here, but because you want, the molecule that is going to evaporate first is going to be the one with the lower boiling point. So you have this mixture of A and B and so on and so forth, comma, but lowest BP component evaporates or is volatilized first. Okay, and so you have all of this, so the liquid mixture now is depleted in the higher boiling, is depleted in the lower boiling substance, and it's richer in the higher boiling substances. They're not going to come off until later. And so you have all of this gas inside this glassware, and now what is usually done is that you run water in a jacket, you run cold water in this jacket here, cold water in, well, the cold water should actually be over here, cold water in and water out, and you're running water through this, and any of the gas is now experiencing this lower temperature, and it collects and it begins to condense as a liquid. And so this is what you want here, the liquid that was purified liquid. All right, so this is essentially how distillation works. You have a mixture of a bunch of liquids, and some of them are high boiling and some of them are low boiling. You heat them up, you vaporize them, and the low boiling component is going to come off first, and it's going to be knocked down back from the gas phase to the liquid phase, as is exposed in this part of the distillation apparatus that has that cold water. Okay, so that's this is how we like to separate liquids. Now, there is a problem with distillation, and one of the major problems with distillation is the formation of azeotropes. And an azeotrope, this is a constant boiling mixture of two or more liquids. And this can be a problem because, let's say, if you have, say, an ester and water together, though many esters and water form a azeotrope, and let's say that the ester has a lower boiling point than the water does. And so you're thinking that as you heat the mixture of ester and water in here, you're going to be promoting the ester into the vapor phase, and it's going to be the ester that is going to be condensing out, and it's going to be the ester that you have separated from the water. But that does not happen if an azeotrope forms. One of the and so what is going to be coming over here is not the pure ester, but what's going to be coming over here is the azeotrope, which is a mixture of ester and water, let's say. So that so this is a complication that we see when we're trying to distill liquids. And so where can we anticipate this problem is that the azeotrope is likely if the liquid components interact strongly. In other words, we have two liquids. A is a liquid, interacts with B, which is also a liquid, and what you're going to get is the mixture of A and B condense. Right? It's not going to be just pure A or pure B. It's going to be this mixture that's condensing, and so you haven't really affected the separation. And so this strong interaction that we find with these azeotropes, one of the main culprits here is going to be hydrogen bonding. Right? So for example, an ester can form hydrogen bonds to water. Water can form hydrogen bonds to alcohols. Alcohols can form hydrogen bonds to other esters. So it is a complication. So this distillation technique, it's good for separating liquids, but there are problems. One of the other things we can do to separate substances in the laboratory is extraction. And here, what is happening in extraction is that we use a SEP funnel. We use a separatory funnel, which kind of looks like this. And there's a stopcock here. And in here, we have let's say that we'll have the compound that we want to purify, the compound to purify. And let's just say it's in an organic solvent, right? Something maybe like chloroform or methylene chloride or toluene or just whatever kind of organic solvent, but it's also contaminated with other stuff. And so one of the techniques that we can use is that we add an immiscible solvent. You add water. So this is the compound to be purified in an organic solvent. We add water, and water doesn't, water is immiscible with these solvents. So when we add the water, after we add the water, what we have in the SEP funnel now is 2 layers. We have 2 layers. Water is usually, water is denser than most organic liquids, but not all of them. But sometimes we will have the water down here, and here we will have the organic phase. And we're hoping that all of the water soluble impurities have gone into the water, and the compound that we want to purify has remained in the organic phase. So now we add water. So here we have water plus impurities of the water soluble type. And so now we can drain, we drain the SEP funnel. We drain the SEP funnel, and what is left now, what is left in this funnel now is the organic phase. And in a beaker over here, we have our water layer, which has the impurities in it. So this is how extraction works, is that you mix 2 solvents, 2 immiscible solvents, and you're hoping that most of the impurities in the sample will partition themselves between the organic phase and the aqueous phase, or between whatever 2 solvents you're using, and that way you can clean up the material trying to purify by coaxing the unwanted impurities into the second solvent. But the key here is that these solvents have to be immiscible. Of course, one can't dissolve in the other, or else you won't have these 2 layers, so you won't have the ability to separate one layer, these 2 layers from each other. Okay, some fancier kinds of extraction would be something like acid-base extraction. So this is like a fancier version of extraction, acid-base extraction. Okay, and so here you would have some kind of acidic impurity, let's say, or some kind of acidic substance, let's say a carboxylic acid. You have a carboxylic acid, and maybe you have something that is not acidic, maybe something like naphthalene, let's say, and then both of these guys are in an organic solvent. But you want to separate them, you want to purify them. So what you would do here is you add, this is an acid, you add a base, and the base reacts with the acid. So here we could add a base, something maybe like sodium hydroxide. And what happens here is that the acid reacts with the base. You get this, so that's an acid, this is a base. You get this sodium salt of this carboxylic acid. This is called the sodium carboxylate. And this guy is water soluble. Okay, but what does base do to this? Nothing, because this is not acidic. So this naphthalene remains naphthalene, and this is water insoluble. Right, so you add base NaOH in water solution. And so now what you have here in your SEP funnel is going to be something that looks like this. You're going to have the naphthalene will be up here in the organic solvent. You added base to it. Base didn't do anything to it. And down here, you're going to have the carboxylate, the sodium salt of the carboxylate in the in the water layer. And so now you can drain the water layer away, and that's how you can affect the separation of acidic impurities from neutral impurities. And then you can also change this up where you have a base there, you would add an acid. So this is just a slightly fancier version of extraction. But again, it all hinges on having these two immiscible layers, an organic solvent and an aqueous layer, or two solvents that don't mix. So that's another way of separating stuff. Okay, another important technique of separation is recrystallization. And so you run a reaction, you get a solid. So this is used to separate or to purify solids. So you run a reaction and you get like we said before, you get, you mix A and B together, you get C, but you also get D, E, F, and you get all kinds of other impurities that that are left behind. And let's say that what you want to do is separate the solid. So this is what recrystallization is used for. So you have the flow chart here would be the impure solid, right? And now what you want to do is you want to add hot solvent. You want to add hot solvent. And so now you have this all dissolves. This dissolves. And now you want to cool it down. But ideally, the solvent that was chosen here, the impurities are more soluble in the solvent at room temperature than the material you're trying to purify is. So you have the impurities remain in solution. But the solid to be purified crystallizes out. The solid precipitates out. So critically important in this recrystallization scheme is the identity of the solvent. So what you want is something like this. Here's the solubility, right? And this would be low temperature. This would be the high temperature over here. And let's say that the substance that you're trying to purify should be insoluble at low temperature in the solvent, but very soluble at high temperature. So this is what the solubility curve should look like for the solid to be purified. However, the impurities in the solvent, the impurities in the sample, they should all dissolve at high temperature, but they should remain in solution at low temperature. So the solubility curve that you want for the impurity maybe should look maybe something like this, right? That would be the impurity. It's very soluble at low temperature so that when you cool the solution down, it stays in solution. And it should be very soluble at high temperature also so that you get everything to dissolve. So this is another major technique for purification. Okay, so I want to show you some slides about recrystallization. So let's try to do that. No, that's not what I want. This is what I want. Okay, so yeah. So let's say you just ran a reaction and you got the crude product, right? And that's all of this jigsaw puzzle looking thing. But embedded inside that crystal, you have impurity. So this says trimeristin. This is just the compound that is being purified there. So this is the crude. You have impurities trapped inside the crystal. Okay, so now you dissolve it in the hot solvent, and that completely tears this crystal apart. And so now inside the liquid, inside that hot solvent, you have the individual molecules that you're trying to purify and the impurities. Everything has gone into solution. So just like I said with that curve, with those solubility curves, that everything should dissolve at high temperature, both impurity and the solid you're trying to purify. This is for recrystallization. Okay, now you cool it down. You cool it down slowly. You don't take this hot solution and put it right into an ice bath or into liquid nitrogen or whatever. You need to cool it down slowly. And as you're cooling it down, the molecules of the solid you're trying to purify bump into each other. They sample each other's space. They know how they should fit together in the crystal, but you have to give them time to find how to combine. And so here these two molecules are bumping into each other slowly, and pretty soon they figure out how to fit. If you were to take the solution and just plunge it into an ice bath, this wouldn't happen. You wouldn't get recrystallization to be effective at all. And then so two molecules have fit together, and pretty soon everything fits together. And so this is how the recrystallization works. And the mechanisms for this recrystallization, how do two molecules find each other? How do they know how to fit together? Well, there are various mechanisms for that. We have hydrogen bonds, and so molecules are stabilized by the formation of hydrogen bonds. So these molecules have to bump into each other, sample each other's space, each other's three-dimensional structure, and they know how to fit together in the crystal. We have van der Waals interactions, hydrogen bonding, and a whole host of other interactions. And so this is how they eventually form that crystal. Okay, so on Thursday's lab, you're going to be talking with your teaching fellow about techniques of purification, extraction, distillation, recrystallization. Okay, now on Monday is another lab, experiment number 3. This is all about chromatography. And this is another technique of separation and purification. And so we're dealing with two types of chromatography: thin layer chromatography, and this is abbreviated TLC, right? Not tender loving care, but thin layer chromatography. It takes an awful long time to say and to write, so we just always say TLC. And column chromatography. And these two are very much related. And the principle that is involved here is that the substance that you're trying to purify, the substance that you're trying to to separate is partitioned between what is called the support or the stationary phase and the mobile phase, which is usually a solvent. So here we have partition between the support, partition between the support, this is called the stationary phase, and the mobile phase, which is usually a solvent. And chromatography works mostly by polarity. Okay, so you remember polarity from Gen Chem. Polarity is an imbalance of electrical charge that a molecule exhibits when atoms of different electronegativity get together. So this, so what is happening here would be something like this. In TLC, in thin layer chromatography, you have a plate. You have a plate, and this plate has a coating of silica. It has a silica coating. And this silica coating is, let's say, it could be moderately polar. Okay, and now the plate is immersed in a solvent, right? So there's the solvent. This is a solvent. And let's just say, just for the sake of argument, that this solvent is very polar. Okay, let's say it's much more solvent than the silica plate. Okay, now the substance that you're trying to purify or separate is applied to the plate, right? It's applied to the plate, right? This is the compound to be purified. This is called the analyte. Plus, there are impurities in here. And now what is allowed to happen is the solvent is allowed to move up this plate, and depending on what the analyte is and depending on what the solvent is, the components of this spot are going to either, the analyte or in the impurities, what they are doing is they're choosing to move with the solvent if they are polar, right? Because a polar substance likes a polar solvent, choosing to move with the solvent or remain on the silica. So if the impurity is very polar, what you're going to see later is something like this. Is that the very polar impurity, moved with the solvent, but let's say the less polar analyte didn't move as much. So this is how you can affect separation using this technique of thin layer chromatography, is that you have the stuff you're trying to purify here, and this has contaminants in it, and you choose the solvent which will move the impurities by a different amount than it will move the analyte that you're trying to purify, all based on all based on polarity differences. Okay, so I'm going to try to show you an animation which shows this. Okay, so before we begin, so there's the silica surface, right? It could be moderately polar. And I have two substances on here. One of them is a polar molecule and one of them is a non-polar molecule. And I'm going to allow polar solvent to sweep past this coating of silica. And so what this animation is supposed to show is that the polar solvent is going to move the polar molecule farther and faster than it's going to move the non-polar molecule. So at the end of the experiment, the polar molecule is going to be way the heck up here, and the non-polar molecule will hardly have moved. And this is how we can affect separation using chromatography. It's all based on differences of polarity. Okay, so let's see if this animation works. Let's see what this looks like. Okay, so begin the polar flow. Oh, you see how the polar molecule is jumping and moving a lot faster and a lot farther than the non-polar molecule. So at the end of the experiment, what you're going to get is that the polar molecule will have moved very far. The non-polar molecule will have moved by a small amount. And so this is how we can affect the separation of different substances using this chromatography. Obviously, polarity is crucially important. So let's talk a little bit and remind ourselves about polarity. If two atoms of different electronegativity, combine, a bond dipole is created. So for example, hydrogen and chlorine. Who's more electronegative? Chlorine is, right? So when hydrogen and chlorine get together, most of the electrons, because electronegativity is greed for electrons, most of the electrons gang up near the chlorine. So if we had a little microscope, this wouldn't be possible, but if we had a microscope and we could look at the electron distribution in this hydrogen-chlorine bond, what we would see is most of the electrons are closer to the chlorine, right? So this would be electron density. Another way of representing this bond dipole would be, frequently we draw an arrow pointing toward the more electronegative atom, and we cross the opposite end of the arrow. And this cross here is not just for decoration, but because if we obscure the arrow, we see a positive charge. Electrons are negative. This is saying that most of the negative charge is on the chlorine side of the molecule, and the electrons have quit the hydrogen side of this bond. They're mostly ganged up near the chlorine. Okay, so that's what a bond dipole is. The vector sum of the bond dipoles. This is called the dipole moment. and its symbol is the lowercase Greek letter mu. And if the dipole moment is equal to 0, that is a non-polar substance. And if the dipole moment is not equal to 0, that is a polar substance. So do you folks remember how to add vectors? Let's go through that. Okay, so now let's look at some organic, let's look at some inorganic molecules. For example, the polar molecule par excellence is water, right? Who's more electronegative, oxygen or hydrogen? Oxygen is. So there's a bond dipole pointing toward the oxygen atom. Who's more electronegative, oxygen or hydrogen? Oxygen is. So there's a bond dipole pointing toward the oxygen. The vector sum of these two bond dipoles, that's the molecular dipole moment. And because the electronegativity differences between oxygen and hydrogen are very big, we add these two vectors and we get a huge whopping dipole moment in that direction. So water is a polar molecule. Its dipole moment is very, very large and not equal to 0. Okay, but now let's compare that to carbon tetrachloride. Well, we need to know something about hybridization and about shape, because the molecular dipole moment is the vector sum of all of the bond dipoles. So this CCl4, the carbon atom, is sp3 hybridized. It's a chicken foot. It's looking like this, something like that. And now what about the bond dipoles? Who's more electronegative, carbon or chlorine? Chlorine is. So there's a bond dipole that points toward the chlorine. 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 And now it's pretty hard to, maybe it's hard to see from this drawing, but if you were to add all of these vectors up, what you would get is a vanishing dipole moment. So that when you add up these two vectors and you add up these two vectors, add up all of these vectors, because of the shape of the molecule, this guy has zero dipole moment and it is non-polar, right? So this would be a compound, this would be a substance or a solvent that you could, to separate it from other stuff, this is by chromatography, this would be the major consideration here, that it has no dipole moment. Versus something like methylene chloride. Okay, does that have a dipole moment? Is this a polar substance? Oh my heavens, yes. The shape of the molecule is everything, right? So that carbon atom is sp3 hybridized. It's a chicken foot. Hydrogen and carbon, their electronegativities are very close together. So essentially, this bond, although there is a dipole moment, carbon is more electronegative than hydrogen. There is a dipole. I mean, this does have a bond dipole, but it's teeny tiny, right? I'm going to draw it like that. It's teeny tiny because the electronegativity differences between carbon and hydrogen are small. This is teeny tiny here. But chlorine is much more electronegative than carbon. So this has a bond dipole and it's big. This has a bond dipole and that's big. And we can essentially ignore these carbon-hydrogen bond dipoles. The only thing we have to consider are these carbon-chlorine dipoles. And when we add these two vectors, we get a pretty substantial dipole moment that points in this direction. On your Avogadro, this also will show you the dipole moments in the display settings here. So this guy, his dipole moment is not equal to 0. This thing is polar. And the bigger the dipole moment is, the more polar the substance will be. So the chromatography, this is all based on polarity. How does the stuff you're trying to separate and purify, how does its polarity compare to the polarity of the support? And how does it compare to the polarity of the solvent that is washing through the, over the support? And if you choose the right solvent, you can get a pretty good separation. Okay, so that's all I have for you today.